Okay, good afternoon and welcome to our event, Powering the Future, Advancing Battery Storage Through Innovation. My name is Michael O'Donovan. I'm a member of the Electrical Division, and the Electrical Division are pleased to be your host this lunchtime as we explore cutting-edge developments in battery energy storage, which is a key enabler of more resilient, low-carbon energy future. Just a quick reminder that our AGM is also taking place on Monday, the 12th of May. That's at 1700 hours or 5 on Monday, again, the 12th of May. Everybody's welcome to attend, and we warmly encourage you to join the committee or share ideas for the year ahead if you're a member of Engineers Ireland, especially in the electrical area. I'd like to thank Sinead Quinn Phillips for organising this event from Clyde Road, Ed Arnott, who's the secretary in the electrical division. He'll be in the background taking the questions. And my colleague Michael Ferreter at MTU, who helped me organise this event. So to this talk, we're delighted to be joined by three experts. They are Derek Browne. So we have Derek Browne, who's the project director. He manages full life cycles deliveries of battery energy system projects across the region. We also have Lucy Plant, who's a sales director, leading strategic partnerships in both Ireland and the UK. And we also got Nosa Aghahowa. He's a sales engineering manager. So each speaker will share their insights into innovation, implementation, challenges, and opportunities in this rapidly evolving sector. I suppose what's important, please feel free to submit questions in the Zoom question and answer box throughout the session, and we'll address them during the question and answers session at the end. So I would now invite our speakers to start the talk. So thank you very much.
Thank you, Michael. Thank you for everyone's attention today, for this opportunity to give you a little bit more information about battery energy storage, some on Fluence, but also the advances in this technology and how they can contribute to Ireland's net zero ambitions. If you want to go to the next slide, Nosa. So I'm going to start with a very brief introduction of who Fluence are and where we're active in Ireland. We're then going to give a high-level introduction to battery energy storage systems, so what they are, how they work, and how they can deliver to support the electrical grid in Ireland. We'll then touch on innovation safety, particularly fire safety, as we're seeing that's a topic that's coming up in multiple discussions with our clients in Ireland. And it's an area that Fluence is really spearheading and leading the way in respect to innovation in our systems and education in the market. And then Derek's going to come in at the end with some case studies for the projects that we've completed. And as Michael said, we're going to have an opportunity for Q&A at the end. Next slide, Nosa. So who are Fluence? Where do we come from? We have over 15 years of innovation experience in the energy storage sector. We are originally a AES and Siemens company. Those two organizations moved together to form Fluence in 2017. We were involved in the first lithium-ion battery in 2008, and we've continued to innovate within the industry from then, starting with our advancing system, which was a 40-foot containerized solution. We've moved on a long way from that, developing bespoke systems, really looking at new chemistries, evolving the chemistry to a more safer technology. So LFP is the chemistry that we're using today, and Nosa is going to touch on some of that innovation and the chemistry behind these systems, and looking at bespoke enclosures for the systems as well. This is all accumulated in the launch of our Smart Stack system, which we launched in February this year at the Energy Storage Summit in London. That is a modularized, containerized system, which is designed both for noise mitigation and fire safety to give you a high-density, deployable solution, modularized, that can easily be deployed to the field. If we want to go to the next slide, Nosa. So really, there's no substitute for real-world experience when it comes to energy storage. As we said, as Fluence, we've been around and active in the energy storage market since 2008. We have almost 39 gigawatt hours of deployed and contracted energy storage systems across 260 projects and 47 different energy markets. That means we've got a really deep expertise in energy storage, in how this can be utilized and monetized within different electrical grids to deliver the best support and solution for the grid, but also the best returns for the operators themselves. If we want to go to the next slide. This just gives you a little bit of an overview of Fluence's experience in Ireland. So in Ireland right now, we have just over 1 gigawatt hour of installed energy storage. Of that, Fluence have installed over 15 projects and around 900 megawatt hours of storage. So we've really demonstrated quite a strong commitment to Ireland. We have a large staff there. We have a reasonable sized staff. We have 15 staff based in Ireland. I myself and Derek are both based in Ireland, and we have a full team of operations and support staff in country. Our support of Ireland is really supporting with the transition to this low carbon economy, helping Ireland to achieve their net zero goals. Nosa is going to touch on that a little bit when we talk about how these systems can really help with integration of new renewables, helping with balancing of supply, mitigating that intermittency that you see with renewable energy sources, and providing fast-acting frequency balancing services. And then at the end, Derek is going to talk about some of the partnerships we have for these projects. So ESB with our Aghada and Poolbeg systems. The Aghada right now is the largest battery in Ireland that's supporting both grid stability, renewable energy integration. We also have the Castlereagh project here with Energia. Bordnamona is with Cloncreen. Kilroot, you might think, well, that's a very small battery. What is that doing there? It's only 10 megawatts, 10 megawatt, 5 megawatt hour system. It was actually Ireland's first battery. So it was done with AES in 2017. And we actually decommissioned that system last year. So it's the only battery so far we've taken in Ireland all the way through the life cycle of commissioning to decommissioning. Now that was decommissioned early due to an incident at the site. So that is not the life expectancy of the battery. But it means that we have that full experience of taking a battery, monetizing it, commissioning it, operating it within the market, and then keep it at the end of decommissioning it. How do we do that safely? How do we recycle the content where we can? And then how do we move that forward? With that, I'm going to hand over to Nosa just to give you a bit of an introduction to the battery energy storage systems itself.
Thank you very much, Lucy. So I'll be talking through a very broad topic, the technical aspect of battery energy storage, and I'll try my best to keep it under 10 minutes and hand over back to Lucy and Derek. So I'll be talking through the need for battery energy storage, its key components, how it all works together, the important performance metrics that we use to evaluate batteries in the industry, the services provided by the batteries to the grid, and the current challenges that we also face in the industry. So starting off with why we need grid scale energy storage. Now, the biggest driver really is the ambitious decarbonization targets, particularly in Ireland, where electricity generation accounts for 23% of the total carbon emissions. The current goal in Ireland is to achieve 80% renewable energy generation by 2030 and reducing the electricity carbon emissions by 75% compared to the 2018 levels. Now, of course, achieving this means integrating more renewables like wind and solar to the grid. And with more of this intermittent generation, we're going to need the capability to store and release excess electricity on demand. Now, increasing the capacity of renewables in the grid will impact the grid strength, its stability, and its resilience. And batteries are very capable of mimicking the behavior of traditional generation assets to provide grid stabilizing services, which I'll talk about in later slides. But right now, renewables only account for just less than 50% of the total electricity generation in Ireland. So we're making very good progress, but still some way to go to reach the targets in the next 5 years. And the deployment of batteries will be very critical to achieving these targets. Now we know why we need energy storage, but how exactly do batteries work? And what are the main components of battery energy storage systems? So there's 4 main components that I'd like to highlight. The first is the battery cell itself. Now, this is the fundamental unit of the battery where the conversion of chemical to electrical energy takes place. You've got your power conversion system or your inverter, And this converts the stored DC electricity in the batteries to AC electricity when the battery is being discharged, and then from AC to DC when you're charging the battery. Now, there's also the thermal management system, which is a very important component because the internal chemistry of the battery cells are very sensitive to temperature variation. So when the battery is idle or when it's being charged or discharged, the thermal system ensures that the average temperature of the battery cell is kept at a sweet spot of around 20 degrees Celsius. If it's too high or too low, the battery will perform inefficiently, and this can also compromise the expected life of the battery cells. And the last thing I'd like to highlight is the battery management system, or the BMS. Now, this is basically the brain of the battery. It's just an electronic control unit that monitors and controls things like the cell voltage, the cell temperature, the cell current, and it ensures that the battery is operating within its limits. And the BMS is also capable of communicating with external control systems like a SCADA or energy management system. Now, all four of these components that I've highlighted above, they make up what we refer to as the best core. Now, other components like transformers, switch gears, distribution panels, they're also part of the best plant, but they're not normally classified under the core terminology. We also have DC blocks and AC blocks, and this just refers to the kind of electricity output that we get from the battery enclosure. So in the slides, you can see a top view of the typical BESS core with the components, with the core components highlighted in yellow. So what we've shown is a DC block where the output of the battery enclosure is DC electricity, and then that connects directly to an external standalone inverter, which you could see. And for an AC block, the battery enclosure output would be AC electricity, and then that connects directly to the transformer. So we would have smaller string inverters, like I've shown on the slides as well, that are internal to the battery enclosure itself. So before going further into the battery performance metrics, I think it will be useful for us to briefly touch on the energy conversion mechanism that takes place within the battery cell. So on the slide, we have two diagrams on the left that illustrate the charging and discharging process. So essentially, the battery cell is made up of two current collectors or electrodes. You've got your negative electrode, which is the anode, and the positive electrode, which is the cathode. And both of these are submerged in a liquid electrolyte. Now, during the charging process, the negatively charged electrons from the external power source would move towards the anode. And then this, of course, attracts positively charged ions within the electrolyte to move from the positively charged electrode, which is your cathode, through to the anode, and that basically charges the battery. Now, the reverse happens when you are discharging the battery. So when it's plugged in, the positive ions will move from the anode in the electrolyte towards the cathode, and the negatively charged electrons in the external circuit would move through the external circuit to the cathode. So this movement of ions and electrons is what causes the flow of electricity in and out of the battery. So the chemical properties of these materials that I've just mentioned make the electrodes and the electrolyte basically determine the performance of the battery. And we'll look at those in the next slides. So a couple of metrics that are used to describe the performance of the battery are the energy capacity. Now, this is just the total electrical energy that's stored in the battery, and we express that in megawatt hours or kilowatt hours. Power is the instantaneous discharge capacity that's expressed in megawatt hours or kilowatt hour, or in megawatts or kilowatts, sorry. Duration is the length of time that the battery can continuously supply its rated power. And the C rate is just the inverse of the duration. So that's just the speed at which the battery can be charged or discharged. If you hear about a cycle, that just refers to a complete charge and discharge of the battery. And of course, the state of charge is just the percentage of energy that's available in the battery itself. Now, batteries degrade when the internal resistance builds up within the cell and inhibits that flow of positive ions through the electrolyte in the cell. So things like time, temperature, the way we operate the battery can cause this internal resistance to build up within the cell and basically degrade the battery. So your state of health is just a measure of the remaining useful life of the battery. As I mentioned in the previous slide, of course, the chemical properties of those raw materials used to make the cell defines the characteristics and the performance of the battery. So two prominent battery types you would hear about in the industry right now are lithium-ion cells and sodium-ion cells. Now, an example of the lithium-ion cell is the LFP battery, where the cathode material is made of a combination of lithium, iron, and phosphate, LFP, and the anode is made of carbon graphite. In a sodium-ion cell, on the other hand, the cathode is made of sodium, nickel, iron, and manganese, and the anode is also made from a carbon-based material. So all these materials have different chemical properties that impact things like, the energy density, the life of the battery, and of course, the cost of the battery technology itself. At the moment, LFP batteries are the more mature technology. They've got very high energy density, which makes them very great for places where space is a constraint. And the sodium-based batteries, they're still very new, still emerging. They're a lot less dense than the LFP cells, but they are cheaper due to the abundance of raw materials that we've got. I'd briefly like to run through the capabilities and services that batteries can provide to the grid. So like I mentioned earlier, batteries are able to mimic the behavior of traditional generation systems like gas turbines, and they can respond much, much faster to disturbances in the grid. So this makes them very well suited for providing frequency services like fast frequency response, where an asset is supposed to dispatch power within 150 milliseconds of a frequency disturbance event. So because batteries are fully electronic without any moving parts, they can ramp up their power very quickly and very accurately in less than 150 milliseconds. Gas turbines, on the other hand, they have rotational moving parts and they can take between 10 seconds and a few minutes to mechanically ramp up their power output. So I'd also like to talk about some challenges. Of course, there's no technology that comes without its challenges, and some that I'd like to highlight are costs. Now, despite the declining raw material costs for batteries, the capital expenditure on some battery projects are ranging between 250 to 350 euros per kilowatt hour. But again, batteries don't have any moving parts, so the operating expense is extremely low compared to other generation assets. There's still a lot more room for improvement when it comes to things like obtaining grid connections and planning permits. Long lead times for essential equipment like transformers are not exclusive to batteries alone, but this also impacts the timeline for delivering a battery project. And finally, there's more to do when it comes to tracking and quantifying the carbon footprint of batteries throughout their life cycle. But there's been very good progress on this recently. The EU has just introduced regulations for a mandatory battery digital passport, which basically tracks things like the product information, the source, and the carbon footprint of the batteries. And we're going to see this becoming the standard across the industry in a few years. So in conclusion, the future looks very positive for batteries. And as the grid continues to evolve and take on more renewables and shift to a more digital type structure, fast-acting batteries are going to be key to providing the critical services that maintain grid strength and resilience. And of course, the battery industry has been constantly evolving at very high pace. We've moved a long way in a very short time, and innovation and safety have been the main driver for this. So I will stop here and pass it back over to my colleague Lucy to speak more on the topic of innovation and safety. Thank you.
Thank you, Nosa. Yeah, as Nosa touched on there, we felt we couldn't give a talk about battery energy storage without addressing some of that, particularly the safety component and fire safety. As we know, within all markets, Ireland is no different to the other markets that we work in. Fire safety is something that we're seeing becoming more and more of a concern for our clients and the communities themselves as well. So as these planning applications go in for energy storage systems, you're seeing more the local planning, the local fire brigades, the local communities wanting additional information to understand what is the risk for this. You see a lot on the news with a Tesla car, for example, and if there's a Tesla car, say, fire incident or another electric vehicle safety, and with that brings that level of concern. So with Influence, a lot of the innovation we've done has been around safety, ensuring that we understand these systems, we comply with all of the regulation that is out there, and that we can develop documentation that we can use both to train first responders for how they can respond if one of these events occurs, and then also to help and support with that community engagement and education. If we go to the next slide, one of the key things to understand is that not all energy storage sites look the same. As Nosa touched on, there has been a great degree and a high degree of innovation, and the technology has come a long way, even within a very relatively short space of time. So even if you went to multiple energy storage sites, chances are they wouldn't all look the same. They would look different. You can see some of them will be warehoused within a warehouse or a building. The first system we had in Ireland at Kilwoot was one of those building-based systems. The systems themselves then moved to the containerized solutions. So modern batteries then on the right-hand side, they're now incorporated instead of in just a 40-foot container. These are now specifically made fire-resistant units or containers, and they incorporate multiple levels to be able to detect, prevent, and then contain any sort of thermal runaway. The battery chemistry is another area where we've seen a lot of innovation within the energy storage space. Nosa talked about there with LFP moving to sodium ion, some of the new flow technology that's coming in, and how we're trying to continue to innovate in that chemistry space. But even in the basis of the last few years, the systems themselves have moved away from NMC or nickel manganese cobalt cathodes, so that battery chemistry, to more towards lithium iron phosphate or that LFP battery chemistry. LFP is thermally more stable and less likely to go into a thermal runaway state. And we're continuing to see that innovation as we look towards sodium and some of the other new chemistries that are coming in. And to go to the next slide, Nosa. And I'm going to go through this very quickly. I know Nosa spoke about some of the components within the system, within the energy storage system. So you have the individual energy battery cells. Those cells go together to form a module. So we have multiple cells that are then put together to form a battery module. That battery module goes into a battery rack or battery pack that then will go into the large container. Something to be really careful of, the terms of battery cell and battery module, they're kind of used intermittently, so they're intermingled together. But the module itself is composed of multiple cells. There is battery management system on top of that, again, as Nosa touched on before. The battery management system itself, the Fluence, we only buy the cells from third-party suppliers, meaning that our battery management system is a Fluence-based battery management system. That means that all of the controls of the electronics, software, within the energy storage system are free from components of countries of concern. So that's going to help protect against things like cybersecurity attacks or mitigates against policy issues with some of the governments now introducing new local content requirements. This is critical infrastructure. Therefore, we have to make sure it is secure and it is safe. The battery management system itself also gains a really key component for monitoring and control of those battery cells. So it allows us to actually identify and prevent issues that could cause a fire early on to try and stop that from even happening. We integrate artificial intelligence into this battery management system so that we can monitor both with humans, but also digitally, all of our energy storage systems 24/7. So we can try and see before a cell goes into a thermal runaway state, we can identify that cell, we can isolate that cell, and we can stop that thermal runaway state occurring. We go to the next slide, Nosa. So some of the key terminology you'll hear if you hear fire safety and a reference to batteries are off-gassing and thermal runaway. These are chemical events. So the batteries themselves, if a battery is damaged, if it's overcharged, or if it's used beyond its life, and again, we say usually about state of charge, as Nosa touched on there, as the battery ages, the battery cell itself will become less efficient. When it gets to about 60% of its original charge, that's when you can start potentially having issues with off-gassing and thermal runaway within those cells. In this case, the first step in any sort of thermal event would be this off-gassing. So you'll see the breakdown of the cell and you'll get initial release of gases. These gases need to be released in a controlled manner in order to avoid explosion. So a lot of the work Fluence will do and the testing work we do is to understand how we can, what gases come off first of all. So we buy the cells from a third-party provider. We will actually test those in our battery lab within California. We will heat those up and we will measure the gases that come off. I will say about 80% of the time, the manufacturers give us information on what those gases should be. We don't always see that within our lab. So when we do those testing, we're going from the ground up. We want to understand what those gases are. We then build that into a module, and we want to understand when those gases are released from a module, what is the quantity, and then we'll understand how do we mitigate and how do we release that gas. The next step in any sort of thermal event would be a thermal runaway. That's when the temperature inside that battery increases uncontrollably and the battery gets too hot. It starts then this chemical chain reaction that causes it to keep heating up, and eventually you will have a fire. You'll experience a fire event. There is no amount of gas suppression, gases or foams that can stop that event. It is a thermal event. It is a chemical event. And once this thermal runaway starts, the only option then is to let the system burn. If you try and put water on it, if you try and put any sort of gas or foam on that, all you're going to do is delay and extend the event. That's why Fluence's approach to fire safety and to fire events within these systems is always a let it burn philosophy. Within Fluence, we have switched from an if to a when mindset when we're doing safety planning. The reason we've done that is this approach assumes that an event is inevitable, not optional. So it's encouraging everyone with Fluence to really be prepared for when an event occurs, accepting that it's our responsibility to be ready. The chances of one of these events occurring is extremely rare. And so far with Fluence, as you see, we've got nearly 39 gigawatt hours of installed capacity. We have not experienced within any of our LFP cells any events to date. If we go to the next slide. So how does again, we talked about it there, the stages of an event. Ideally, you would want to mitigate the event before it occurs. So if we see one of those battery cells is running hot within our battery management system, we'll be able to pick that up. We want to isolate that cell and de-energize it so that that does not continue to be an issue. If we're not able to do that and the event continues to progress, the first step will be that off-gassing. Again, we're going to have multiple detectors within the system itself to be able to detect when this event is occurring so that we can monitor it. You do not want to, so the time frame between this initial off-gassing event and the thermal runaway event and then flames being seen, from our full-scale burn tests, we know that's up to 6 hours. So our alarms can go off. We will detect that an off-gassing event is occurring, and therefore we believe that the system is going into potential thermal runaway. You do not want to introduce any air into that system. So you don't want to open up any doors and look inside. You have to leave that system closed and let that continue to event, hopefully isolating it and preventing it from continuing. Within LFP cells, what we do see, although off-gassing can occur, it is very unlikely that that would move to a full thermal runaway event, although it can do, and that is what we have to prepare for. So what you want to do is actually monitor that remotely. Fluence's new systems, so the GridStack Pro and our SmartStack systems, our latest product offerings, have integrated gas sampling manifolds at the top, middle, and bottom of each container. That allows first responders to have eyes inside that container to monitor those gases as they build up without having the need to open the door and then risking any sort of explosion. Once the thermal runaway does occur, again, we want to make sure, or if it does occur, you want to make sure that occurs in a controlled manner. So as the gases build up, you want a way to be able to release them from that container in a controlled manner. You want the system to pop like a balloon, not explode like a grenade. So that's where some of the design features that Fluence have integrated into our containers really support with that. We have deflagration panels, both active and passive deflagration panels within the system to make sure that that gas is released in a controlled way, and I'll touch on that shortly. One thing to note, and we do a lot of training of first responders, Fire Brigades Association. We did a fire safety breakfast at Crow Park in Dublin last year, where we talked to the Dublin Firefighters Association. We also go around and educate local fire brigades on how to deal with these systems. One thing to note, we do not recommend using water on these systems. It's a highly energized system, although you can isolate that. If a first responder comes and they come with their hose, put a stream of water onto that battery, they become the grounding rod for that stored energy. So we really want to make sure, and our message to the industry is, do not put water on these. Our recommendation is just, if a system does go into thermal runaway, to let it burn, leave it there. We have controls and bundling in the system to make sure that you can, any sort of environmental impact from that is minimized. If we go to the next slide. So these are some of the codes and standards that we all have to, within the energy storage sector, comply with. The UL 9440A is the most recognized. This is the standard for thermal runaway testing. So the requirement here is to test at a cell, module, and unit level. Fluence actually go a step further than that. We do a full-scale burn test. So we've completed 7 of these. We started doing them in 2022. So what we do there is we actually, first of all, as we said, we start with a cell test. We burn a cell. We then go and burn the module. And then we actually get the whole container and we force that into a thermal runaway event. We use that to understand what happens during that event, ensure that all of the safety and measures we have in place work as they're supposed to. We also use that to understand the spacing. So when we are doing layouts and planning applications for these batteries, the spaces between enclosures, back to back, road to road, side to side, is all defined by this safety testing that we do. The NFPA 68 and 69 specifically address those deflagration panels. So when that thermal runaway event is occurring and you have that off-gassing, how are you going to release that gas in a controlled way? We go to the next slide. This just gives you an indication from our GridStack Pro system of some of those safety measures that we've integrated. So you can see at the top of the system, the things that look like sunroofs. They are our active deflagration panels. So they're going to open up, or they're the passive deflagration panels. They're going to open up. They are like a sunroof. So the first time that any gas is detected, those are going to open up and they're going to give a way for that gas to be released in a controlled way. More like a kind of chimney, if you like, on the top of the battery system itself. Next to that are the active deflagration panels. Those will, as the pressure starts to build up within this container, those will blast off. So again, that's your popping like a balloon, not exploding like a grenade. Within the system itself, both the internal walls and the external walls are all fire rated. So that means that we're going to try and contain, or we will contain it within this unit. With the newer systems we have, with the smart stack and with some of our older cube systems, we have further modularity within the enclosure itself. And the design of that is to minimize impact. Ideally, within the new product, the smart stack, you should only see one rack or one battery pack at a time that would be lost in the event, in the case of one of these events. So you're trying to minimize that spread and the number of batteries that are involved. If we go to the next slide. This is our deflagration panel, deflagration testing. So this is what we do in an explosion facility in Newcastle in the UK. So we actually measure, first of all, the gases that come off when those cells go into thermal runaway. We then use that information here to do the testing. So we'll actually use the gas itself that you will see from those cells. We will pump that within a dummy enclosure, see that pressure build up, and we want to see those deflagration panels pop up off the top. We want to know, do they work correctly? Do they come off correctly? Does it work in releasing the panels? What you want is that they're the weakest point within the battery. You don't want the doors blowing off the front and potentially either impacting a cell opposite it, or worse than that, potentially going into, say, a first responder who's close by monitoring that system. So we want to make sure that that is working correctly that they're coming off. We'll also produce CAD models for this. So we know the gases that will come off during one of these events. With that CAD model, we can then model the distribution of those gases. So again, if you have a community that is living close by, they can understand what is going to come off, what do they need to be concerned of, if there's a predominant wind direction, how are those gases going to spread before the true thermal runaway event occurs, and those gases are then burned up in the process. If we go to the next slide, this shows our full-scale burn test lab that we have in the US. It's a place called Safe Labs in the US. As I mentioned, we've done 7 of these full-scale burn tests. So every time we have a new product that we launch, or we utilize a new cell manufacturer, and so the cell itself changes, we go and we do one of these full-scale burn tests. As you see here, we have an initiating cube in the middle, and then we have cubes that are surrounding that. What we want to see is, can we contain that within just the initiating cube? How does this fire progress? Again, do the deflagration panels work the way they're supposed to? And then when we do ignite a flame, is it contained within just the initiating cube, or do you have any transfer to surrounding cubes? So we monitor that, we record that, we use those videos for our first responder training, so we can show them a real life example of what this fire, what one of these events would look like. Next slide just shows some of the thermocouples that we have. So again, when we're doing these tests, we are getting as much data as we can. We have a gas collection above the system itself. So all the gases that come off, again, we're collecting those. We understand from the cell level, but you're going to have additional combustible material within that enclosure. We want to understand what gases that produces. Again, so we can use that for education for first responders, for environmental impact assessments, and for after the effect, reviewing how we then control and we clean up if one of these events occurs at one of our sites, and then for community engagement. And you want to as well look at how that and the distribution of that heat. That helps us understand, is the fire rating walls and the amount of insulation we have within our containers sufficient, or do we need to change that? You do see as, for example, we move in cell energy density. So you may move from a 200 series to a 300 series to a 500 series cell. Some of those, depending on the chemistry, depending on the cell manufacturer, will burn hotter than other cells. We need to understand that so we can make sure, again, we have the correct level of insulation in there, and we're not seeing that transfer across the site. Okay, and next slide. Just a quick summary of the impact. So again, we've done these full-scale burn tests, and what we've seen for a 100 megawatt 1 hour system, it was extremely difficult, first of all, to actually initiate thermal runaway within the LFP batteries. We had to force it to do that. The system itself really didn't want to. We did see off-gassing, but in order to get that fire to start, we had to really force that system to go. It was contained with a 3-inch gap between the initiating enclosure and the surrounding enclosures. We did not see any transfer from one cell, from one module to the surrounding one enclosure to the surrounding enclosures, and that meant that you can just isolate and de-energize those particular enclosures, and you wouldn't need to then stop the entire site. The rest of the site can continue. You can then repair and replace those. Finally, we have our smart stack system. So I touched on it a few times here. So this is the direction that we are going with new products and new innovation within the energy storage space. So we actually have the smart skid at the bottom, and then you can see it's got 4 pods on top. Each of those pods on top contains the modules, so the battery cells themselves. The idea with this is both for streamlined deployment, so that you can use a small crane on site, easily transport this, get it to location. It should be, again, modularized. You can see a gap in between each of those little 4 pods on top. That's to minimize the amount of impact should a thermal event occur. It's going to be contained within just one of those modules. Another impact we see, particularly in Ireland, where you have very strict in rural locations noise requirements for these systems, down to 35 decibels at night. Noise can be an issue. So again, by having that skid on the bottom, this is an AC system with integrated string inverters, we're able to minimize the noise that this system puts out. ensuring that it can go and it is suitable for those sorts of locations. And then energy density. So we've moved to where now one of these systems here is 7.5 megawatt hours, which allows us to start looking at some of the long duration energy storage, 8-hour, 10-hour systems. What we actually see in the market is both the price has come down. So what you would see previously a 15-minute system, say in 2008, you can now get a 10-hour system for around that same price. Therefore, all of these other impacts, making sure that the cost of actually deploying these systems, the logistics of getting them site and constructing them is becoming more and more important for the business case for these systems themselves. With that, I'll hand over to Derek just to talk about some of the clients that we've worked with in Ireland and the projects that we've worked with in Ireland.
Okay, so we've seen from Nosa the chemistry of the lithium-ion batteries and the LFP type in particular. He's discussed the application, and Lucy has taken us through safety elements and discussed fire concerns and measures taken. And then we discussed also briefly about the continuous innovation in our smart stack unit. I want to bring you now on a brief journey through the practicalities of delivering such projects. We'll work through the phases and show how ongoing innovation via the smart stack is helping us to speed up deployment. This is a typical installation. This is added to in Cork, 150 megawatt 2-hour system. You can basically see the general components. You've got the cubes themselves, and on one end of the core, you have the telco cabinets and the low voltage distribution panels, and then on the other end, you have the inverter, transformer, and then finally the ring main unit, which effectively connects the system to the grid. There is a Aghada 1, there's another smaller ESB best plant off screen to the right hand side. But this particular one has over 500 cubes with 36 separate cores. And by the way, the cubes in this case and the inverters are all green. That was a planning requirement. So like any project, the scope is defined at an early stage, and Fluence are in a position to offer everything from a full turnkey to what we call a core only. Turnkey is complete EPC right up to the grid transformer, which basically includes everything. We have Core Plus then, which is essentially engineering, supply of the best equipment, installation and commissioning, and then the customer carries out groundwork, site preparation, civils, and the MV and HV works. And finally then the core only, which is a much lighter touch from a Fluence perspective. It's the engineering and supply of the best equipment and includes then final commissioning and site testing. Now, important element of the whole BESS plant is the ongoing operation and maintenance, and Fluence offer performance and availability commitments. Availability commitments typically run about 98%, and we also give guarantees on capacity. And in the DS3 ancillary services market, we have fast frequency response guarantees of less than 150 milliseconds. These will become less important as we move on to the next phase in Ireland, which is essentially the whole long duration energy storage phase. Now we do have a 24/7 monitoring on all the plant in Ireland with an agreed hierarchy of contacts and notifications. We've also dedicated a service team with guaranteed response times, and in training, operator training, usually around our user interface and our AI-assisted Nispera system, which Lucy mentioned earlier as well. Ongoing collaboration with planning authorities, local, the fire authorities as well, is very important to get the message out there and to alleviate any concerns people might have about battery energy storage systems. On the logistics side, it's important to get delivery correct. Our cubes arrive containerized and they're extracted with forklift onto a flatbed. Usually there are 3 cubes to a container, and in order to reduce double handling, we put the the flatbed is delivered straight to site where it's offloaded and craned, where the cube is craned directly into place. The rest of the equipment is European sourced and is usually delivered directly by truck from the continent. Lately, we've been locally sourcing in Ireland the distribution panel and the telco enclosures. And all our sourcing directives align completely with the EU requirements. I just want to bring you to a quick detailed view of each cube. And if you look at the bottom, the left-hand photo in the bottom left, we've got a flexible conduit which allows all the cables to interconnect the line of cubes. We've got a strobe unit to indicate if there's a fire or overheating within the cabinet itself, and it helps firefighters and operators to pinpoint the exact location of the cube. Each cube is fused with physical fuses for protection and a disconnect switch allowing maintenance or isolation of that particular cube. There's a fast stop button on each cube as well, which allows an orderly rundown of that particular core, and most importantly, physical door lock, padlocked door, given that the BESS units are normally located in a fairly remote location and would be unmanned. So it's very important from a security perspective. There's a UPS system built into each cube to allow, again, an orderly rundown in the event of loss of power. And the cable connection interface down the bottom right-hand cover, which I'll show you in more detail later on. On the door view, that's when you open the door. On the inside of the door, there's a HVAC unit, and the job of the HVAC unit is to keep the atmosphere within the cube at an optimum level and avoid any sort of condensation as well. And finally, then the chiller unit, which circulates coolant, a mix of glycol and water, around the battery modules, again, to keep them at an optimum operating temperature. The interconnection panel, which I mentioned earlier, just connects the comms, the LV power system, which is a single phase, and then the DC bus connectors, which are at the top of the cubes. And you can see from the photographs at the bottom the flexible nature of these bus connections to allow for minor differences in distances between the cubes. What I'd like to do then finally is to just show a brief comparison, if you like, between the current generation, the grid stack, and the deployment of the next generation smart stack configuration. Well, overall, given that the energy density of the smart stack unit is much higher, that results in a much smaller footprint on site, and allows us to use maybe secondary sites and maximize the asset in terms of delivering power to the grid. And then from a logistics perspective, overall, we have fewer components on the smart stack because, as Lucy mentioned, the string inverters and the coolant systems are all built into the bottom skid itself. So we've fewer pieces to move around site and to deliver. And because we've less cranage and reduced interconnections within the system itself, we can make the installation work in a lot more efficient sort of way. The logistics side and the installation side is combined, if you like. We have a just-in-time delivery arrangement, and it avoids the double handling of all the equipment. Then on to the cold commissioning. On the smart stack configuration, all our interconnecting cables are now pre-terminated and tested. In the case of most of the modules, the coolant is pre-filled, so that saves us a lot of time on site, particularly if you had 500 cubes to fill with coolant. And we now have a team of dedicated technicians whose job is to make sure that we have a fully integrated system ready to energize. Post-energization then brings on the hot commissioning process, where we have where our dedicated site engineers are on site, but we've also increased the remote activity as well for process and problem resolution. So given a typical 25 megawatt site with, say, a 2-hour duration consisting of over 90 cubes on the grid stack configuration, we could probably improve our delivery from typical 18 weeks down to about 13 or 14 weeks, which has a huge impact in terms of getting a project to commercial operation as well. And then, of course, then following that, there's always the testing, the performance testing, the grid code compliance, and specific customer checks. So I hope that's given a good overview of our smart stack configuration and innovation through the battery energy storage system in general. Thanks very much.